Hello, everyone. Thanks a lot for joining us today. Today we will be talking about one of core Java data structures that can be really useful in some cases, and we will show you an example of a task where you can use this data structure for to make your code more efficient. I don't think that's I think everyone knows Ivan, so without further ado, we can start our presentation. And I remind you that you can ask all your questions in the chats on the YouTube or on the We Are Community platform. We will try to cover all the questions.
Yep. Hello, everyone. As Daniel already said, today we will talk about one very important data structure. But first of all, let's start with some real example. Okay, so I hope that you can see my screen. And today we will talk about books. Let's say that we are backend service of some large bookstore, so we are selling books. And one day, manager came to us and asked about statistics. We should provide statistics about book sales. So, what is the most popular book of the year? Maybe not the first one, but 10 most popular books, 12 most popular books, and etc. So we have information about all the cells. So as an input, we have an array where we have different books. Here, as you can see, we have book A 2 times. So it means that it was sold 2 times. And book B 3 times and book C 1 time. And we should return 2 most popular books. So in our case, these books are book A and book B. One more note. We don't care about books order. So as you can see an example, book A 2 times, book B 3 times, but we are going to return them in such order, book A before book B. So it is okay. So we don't need to return them in the descending order of the cell count. So let's try to solve this task. I hope that you can see my IntelliJ. So let's start with model. Our book item model is very simple. We have just a book item ID and name of the book. Nothing else. Actually, and we have some service for that. Let's check it out. So we have implemented some method which is called get top popular book items. So as I said before, we have some input list of book sales and the size of our result list. So we have implemented solution using Java Stream API. So first, we need to calculate book frequency. So we need to know how many times books A, B, C, D are present in this list. So we are just doing for each for book items list and using compute method. We are just please go away.
You can use
using
escape to close this window.
Okay. Thank you. And using a compute method, we are just increasing book item number if it is so by using this method, And here, using Stream API, we are going to get entry set, sort them by value, and we need to do reverse because we need top most popular books. Then we should do limit, and then just map to initial book item and return it. We have some tests for that. Let's check it out. So here in the test, I have some test data prepared. So we have 6 books with different IDs and names, and we have a statistic list. So let's check book item count. So first book, as you can see, it's highlighted. So first book 3 times, second book 4 times, third 2 times, fourth a lot, like 5, fifth only 1, and 6 a lot. So if I'm not mistaken, the most popular book is the 6th one, then it should be like 4th, and then maybe 2nd. So let's check it out. Let's actually get the top 2 most popular books.
Yeah, while it runs, we have a question. Can we do that in one stream? Actually, yeah, using the methods grouping by and then collectors
Yes.
counting, it will work exactly the same, but maybe a little bit slower. So it's like implementation detail, not an important here.
Yeah. So as you can see, the most popular books are The Man in the Sea and It. So 6th item and 4th item. So we can change the size, let's say top 5 books, and all the books should be present except maybe 5th book. 5th book, The Great Gatsby was present only once. So it's still running. Yep, as you can see, all the books except 5th book. So as you can see, our method is working fine. But this solution is actually not the best solution, and we can use different data structures to solve this problem. And maybe later, by doing some research, we can acknowledge that other solutions are actually faster than our current solution. So our proposal is to investigate binary heap. What if we can solve this task using binary heap, and our solution will be quicker? So to do so, we need to know what binary heap is. So binary heap is a special data structure which is based on, let's say, on 2 things. First of all, it is based on array. So we will store our heap as an array. We will show you how it will work. And heap itself is a tree-based structure. So when we insert some value into heap, it will be tree-based. So each root should have no more than 2 nodes, and our heap will be filled from up to down and from left to right. These are the rules of binary heap. So let's just try to enter some value. So I will just click insert. So as you can see, now we have the first element. It's 10. And as you can see, our array is also filled. So first element is 10. Let's insert some random value. let it be, I don't know, let it be 15. Okay, so now 10 is still root and 15 is a child of 10. Let's look at the array. Um, heap array has some strict rules. We can find uh, child elements by parent index. So let's say that 10 is a parent. We can find 10's childs in the second in the second index, in the second cell, and in the third cell. Why? Because there is a special, let's say, formula. So to know our child indexes, we should multiply parent index by 2 and increase it for left child by 1, for right child by 2. So let's...
Yeah, this is a formula for a zero-based heap. In this case, we have a one-based, so the formula will be slightly different. It will be just 2 multiplied by index and 2 multiplied by index plus 1. So there is a slight difference, but yeah, it's not that important.
Yeah. Thanks for clarification. So as you can see here, we don't have any value in the zero element and the zero index, but in real life, in Java, 10 will be under 0. So that is why I said that it should be index multiplied by 2 and plus 1 or plus 2. So as you can see now, 10 has 2 childs. So let's add new element. Let it be, I don't know, let it be 7. So let's check it out what will happen. Okay, so what just happened? Initially, 7 was inserted here as a left child of 15. It was 15 here. But then shift up operation was performed. What does it mean? It means that heap has some strict rules, and after each insert operation or delete operation, these rules should be valid. And for min heap, this rule is that each root has to be lower than child's. So as you can see, 7 is lower than 10 and is lower than 13.
Well, actually,
But
the root
previously...
should be the smallest element in the whole heap, not
Yeah,
just...
this is yeah. I was just talking about let's say parent node and child nodes. Yeah. So if we're talking about the root, so yeah, root itself should be the smallest value. So now, if I want to insert 5, 5 will be the smallest. So I would expect that after I will click insert, 5 will be here. Let's check it out. Yeah. So as you can see, heap is filled from left to right. 5 was here, and then we should perform shift up operation to validate that heap is actually correct. We have operation remove smallest. So by doing this, we will remove 5, and the heap will be restructured. Let's do this. So 5 is removed, and we actually have the same heap as it was previously uh, by doing actually shift down operation. What does it mean, shift down? So when we remove the smallest element, uh, the element with the highest index will be placed in the root, and then it will be sifted down into his, let's say, correct spot. So if we place 15 here instead of 7, 15 is not the smallest value. Actually, this is the biggest. So if I remove 7, it should be 10 here, right? Let's check it out. So 7 is removed, 15 is here, but we should swap 10 and 15. And now, again, we have the correct heap.
Yeah,
Mhm.
I will interrupt briefly. I would like you to pay attention to the current array. So we have 10, 15, and 13 in that order. So the array is not sorted because sorting and keeping it sorted would require a lot of overhead. In the heap, we
Yep.
just have the smallest elements on the top levels, but the order of elements is not that strict, so they are unsorted. It allows us to have a better performance in this data structure.
Yep. Absolutely agree. So now we have some basic knowledge about binary heap. Well, let's first of all, let's try to implement it. Okay, so let's open our IntelliJ. So we have some basic skeleton of binary heap class. So we have our array, which is called heap. We have some basic operations already written. So how we can get parent index by some current index. So it should be done like this. As I said, to get left child index, we should multiply index by 2 and plus 1, and right child plus 2. And when we are doing sift down or sift up operations, we should swap elements. For this, we have this swap operation. Okay. So let's start. We have some input array, and we should build the heap. So let's say we have some current index. Okay, this current index, yeah, let it just be for now. So we have input array until we have some elements here. So first of all, we should add this element to the heap, right? So it will be like that. And after that, we should do shift up. Oh, mistake. Shift up operation with current index. So how does this shift up look like? So okay, let's go back maybe to our visualization, and let's enter 5. So let's check 5 swap. So we should check 5 with the parent, right? So here will be parent index, and we can get parent index by our current index if heap index lower than heap parent index, we should do swap.
Yeah, I just would like to clarify that here we are simply using integers. We are not putting some
So
books
yeah,
here just to keep it simple, because the principles of the codes will be the same, but we'll have to get some fields called the comparators. So it's typical to just write it for integers.
Yes,
Yeah.
yes. So actually, so we just swapping once here, but as you saw with the 5 example, 5 was swapped 2 times. First time with 15, second time with 10. So how do we do that? We should actually assign parent index to index, and do that.
We can do it in a while true, or while the parent index is more than 0, so we don't go over the boundaries.
Yeah, let's say while we don't have parent index here, so actually I don't like that. While oh. So now we should actually, I think maybe we should do that here. So
no, if we don't do it in a shift up operation, we will have to call it multiple times from the insert, and it's not very efficient.
Yeah.
I
think
can
it should be
be
just here.
Well, we can be not afraid of calling parent method multiple times. So it can be like while index is more than 0. While index is more than 0, and array and heap in the square brackets get parent index from index is lower than array from index.
Yes, and we should just do that.
Yeah, you didn't write the condition. I think it should be another sign. It should be less.
While index is bigger than 0.
Yeah, while we still are in the boundaries of the array, and while the parent element is less than our element, we swap them. But on the line 19, you should call the get parent index again.
So like this.
Yeah, remove it from line 17 completely. No, from line 17, yeah. And on line 19, paste it again. Index equals get parent index from index.
Yeah, okay, just let me think about it. So here, if we have less sign, then let's say we have here parent 5 and child 10.
Yeah, and we will not go
Yeah. Okay. Yeah. Correct. Okay. So, yep. Um, so we have shift up preparation now. Let's try to implement shift down. So here we just have to have left index.
Yeah, while you're writing it, I will say that there are, well, basically two types of binary heaps there that are essentially the same. These are min heaps and max heaps. They have the same rules for building them. Just in the min heap, the minimal element is in the root, and in the maximum heap, the maximum element is in the root. And to convert one type of heap to another, you can either multiply all the priorities by -1, so what was the largest becomes the smallest, or you can just invert all the comparisons, so use greater than instead of less than, and vice versa. And all the other code stays the same. And actually, yeah, I think on line 16 we should use greater than, not less than, if we are building a min heap.
So actually bigger.
Yeah, if our parent is bigger than current element, we swap them, so
Yeah.
the minimal element goes up.
Okay, so shift down. We have left index, right index, and so maybe not the largest, but if we have heap smallest index. So if left index is correct, it is present in the heap, and heap left index is actually again
Yeah, in
bigger.
that case, it will be another sign.
Why? If left index is so if we have 5 as a child and 10 is a parent, let's say, we should swap
Yeah,
them.
we should swap them. Yeah, we're shifting down. So in these two methods, just the conditions should be different. If you have less than in one method, it should be the greater than in another.
Okay. It's to if statements. We want to know if our current index, our current value, is smaller than any of child's. If is actually bigger. If it is bigger, then we should continue shifting down. So it should be like while true. So while true, if our smallest index is equal to index after our statements, then we should just break, and else we should swap smallest index and index, and index should be equal to smallest index.
I think on line 33, you should get the not heap by index, but by the smallest index. If it was replaced already by the left. No, not here.
Yeah.
Maybe here too.
Agree. Totally agree.
Yeah, so we are trying to find which element is smallest, left or right.
Yep. Yep. So yeah, and this sift down operation is needed if, again, we are removing something. So let's say we have some method public int get min. Okay. So let's say we know that it will be int min equals heap 0, right? Heap 0
Yeah.
is always the minimal element. And then we will assign the last element. So it will be heap.
Actually, we have to keep the track of the length size of our heap. If we just access heap length -1,
Yeah.
it can be an empty space.
That is why the current size field. So be like that, and here and the heap current size. And then we should do sit down.
Yeah, so basically for all the operations, you have to implement sift up, sift down, and then there is, well, you write really simple codes. You just manipulate some basic elements and just call the sift up, sift down. So they are the biggest complexity of the priority queue here.
Yes, totally agree. So as you see, we have implemented basic operations. So Daniela, can we continue with priority queue now? I think we can.
Do we have tests for this queue?
No.
Okay, so yeah, that's the basic implementation. You can implement other methods, like, for example, adding just one element, not building it. It's a very common. Usually the heap the heap doesn't have the methods to get element by index, so it only allows you to access the minimal or maximal, depending on the type of the heap element. In our case it's get min, and also you usually have the method peak that returns the minimal element but doesn't remove it, so you can call it multiple times. And yeah, actually in Java this algorithm is implemented in a priority queue class that is a part of the java.collections framework, and we will now use it to implement this task. The priority queue, it works exactly as we showed you. There is an array of elements, but
let's just check it out. So as you can see, array of elements, some size field, and as you can see in Javadoc, priority queue represented as a balanced binary heap. So two children of q to multiply n
twice
plus 1.
n plus 1 and plus 2 basically. But yeah, this priority queue, it stores not the integers but objects, so to compare them it has to store the comparator interface internally. So that's like the main difference from our heap.
So we still need to know the frequency, so this line is the same, and now we can introduce some record.
We are using nice Java 17 features, and by the way, I think it's a good place for a bit of commercial. If you would like to know what will actually be introduced to Java 21, you can check out our latest video. It wasn't a live event, but just a video on the 4 main changes that Java 21 will bring to us in 2 months actually. There are a lot of interesting things there.
So to use priority queue, we have to implement comparable or to implement comparator interface. So we will just implement comparable.
Yeah, so the queue has to compare elements, and you have two options. Either each of your element has to implement the comparable interface, so it's like it can compare itself to other elements of the same type. Or when you're creating a queue, you can pass the custom comparator. For example, if you cannot control the code where the object is created. So for example, you're creating a queue of standard library objects, strings, for example, they're not, well, no, they are, but some
Oh.
objects that are not comparable. Yeah, but here it's actually looks better if you implement comparable interface. And here we reuse the static methods of integer class that compares and returns -1, 0, or 1, depending on the parameters that we pass.
So our record is ready. Yep. So now we can just do for each for frequency.
Yeah, we have a question. Why static array, not array list, for example? Do you mean the priority queue implementation, or exactly? If you mean the priority queue, I think that array has a better performance than an array list. And when you are implementing some algorithms, you don't care about the performance that much, so it's better to use array list because it has like better checks, etc. But in the GDK codes, every microsecond matters. I think that's the reason for that. Oh, and actually, yeah, it requires less memory because when you have objects array list that references to the array, it requires additional 16 bytes on current versions of GVMs. Yeah, what if you run out of size? Yeah, this array will get resized. So it works exactly like the array list internally. Yeah, so let's maybe describe what happens here. We
Yeah.
create a, yeah,
Yeah.
go on.
So actually, so priority queue is created here. Now in this for each loop, we are just adding each element to our queue, and we have this special statement. Why do we have this statement? So we are implementing minimal heap. Okay, so our root element will be the smallest element, but in the end, we have to return the most popular books. Okay, so when we see that our queue has reached the biggest size which we need, we can just simply remove, and this remove method will remove the root. Okay, so if we know that we don't need the smallest element because our queue has reached the maximal size. So we can simply remove the smallest element and continue without it. And in the end, only the most popular books will stay inside our queue. So that is why we can just map our queue to book items, and that's it.
Yeah, actually, it will work if you don't write this if queue size. Well, if you don't limit the size of the queue and do it only after you insert all the elements, it will work, but actually it will make the performance worse because the queue, it works faster if it has fewer elements. And here, if you understand the algorithmic complexity is logarithmic. So if you have a queue of size 10, it will work like 5-6 times faster than a queue of size 1 million. And by keeping it small, we improve the performance of the program.
Yep. Yeah, yeah, totally agree. So, uh, it seems like our new implementation is finished. So I just wrote the second test, which is identical to our first test, but we are calling different method. Okay, so let's check it out. It should be 5 items without fifth book, if I remember correctly.
Yeah, we have a question. Why don't we use a max queue, one min queue? Because we would like to throw out elements that we are not interested in. If we use the maximum queue, on the top of it, we will have the elements that we actually need, and we cannot just throw them away, and we will have to feed all the elements to the queue and only then get like top 3, top 5 elements, and it will be slower than our current implementation that throws away all the elements that we don't need and keeps only those that are at the moment best. Maybe they will be thrown out later, but for now, yeah, we need them.
Yep, yep. So we can use max heap, but in such case, we can't introduce such, let's say, enhancement. Yes, so we should have the whole queue in this case.
Yeah, and if we
Mhm.
don't use these enhancements, the performance would be roughly the same as with a simple sort. Again, if you understand the algorithmic complexities, it will be n multiplied by log n, and in our case, it's n log k, where the k is the size of our resultant array, and which can be much smaller than n, and well, it will be more efficient. And for example, on the
Yep,
uh, input size of, let's say, 10 millions, it will be roughly how many times? 6 times faster than the sorting.
yep, yep. So if you want, you can try to you can try to check it. So using some let's say testing frameworks, testing tools, you can check the speed, what is quicker, what is faster, and by which
Yeah,
time.
someone asks to share the codes at the end of the meeting. I think we will commit it to the GitHub, and I will share
Yep,
the link at least on the YouTube, so you can check it out in a few hours.
yep.
Yeah.
So as you can see, I already executed our second test, test two, and the top two books are again the fourth book, it, and the man in the sea. So as you can see, our second implementation works fine. So maybe the last thing we uh, so there was already a lot of information about algorithmic complexity. So you can check it just under priority queue wiki page. So what is complexity for different priority queues for binary, for
Yeah, so
terminal?
here we implemented the binary queue. It's the simplest one,
Yep.
and as you can see, it has the worst complexity algorithmic. So it's expected to be worse than other queues. But from what I read, other queues, they have quite a huge overhead. So in real case scenarios, the simple binary queue can be faster than other implementations, but still, if you're interested in the algorithms, I would really suggest you to read at least the binomial and Fibonacci priority queues or heaps. They are really interesting, and I just cannot understand how people invented those algorithms. Oh my god. Yeah.
Yeah. It's difficult to imagine. Yep. So actually, that's it. So maybe we have some more questions.
I don't see any more questions for now. Maybe I will give like 20 seconds to post them. And yeah, while you maybe post your questions, I'd like to remind you that we have a free Java school on mjc.school that goes from the very basics of Java, like creating the main method, etc., and up to advanced stages like the cloud, CI/CD, modern frameworks. And the school is completely free, and you can enroll today for free on mjc.school or do it tomorrow. But why wait for tomorrow? Yeah, that was the second small commercial. Yeah, there is one question. Could you estimate the time complexity of the algorithm you developed? It will be n multiplied by a log n. What did I say? N multiplied by log k, where the n is the initial array
Yeah.
and
So
the
and
size of the initial array, and the k is the size of the resulting array.
yeah. So here, let's say, yeah. Okay. Yeah. So, as you said, I will just maybe place it here like
Yeah.
n book items size k input.
Why the difference? Yeah, the question is, what is the difference between k and n? We, if we have the big input but only a small output, so for example we get 10 million books, we are Amazon, we are selling a lot of things, but we would like to get only top 3 products that we sell. It will have a huge difference, logarithm of k or logarithm of n. Yeah, Ivan, could you please write the complexity for this solution and for the initial? Yeah, so this complexity is not linear. Uh, it will not work as fast as maybe we would like it to work, but it's faster than using a sort. Yes, and we are limiting the size of the priority queue, so the logarithm will be taken from k, not n. It's the main difference here. Yeah, otherwise it will work exactly the same like the sorting.
Yeah. So
Yeah,
so the main difference is that if we need to have the top, I don't know, 3 books, we don't need to perform the sorting of the whole array. We just have to know what the the most popular elements are. So here we are doing sorting, but we actually can avoid it.
yeah, so we don't need to know is this book 100th or 101st, and
Yeah,
we
yeah, yeah.
don't have to perform the calculations to get it. Yeah, it's maybe the last thing from my side that I wanted to say is that the priority queue can actually be used for sorting. It's called like a heap sort algorithm. So you create a priority queue, you feed all your elements to it, and then just in a cycle you get min, get min, get min, and push it to the resulting array. It has a good algorithmic complexity, so it will be n log n, the same as the quicksort, merge sort. I'm not sure if it works faster on modern processors or not. Don't know, but yeah, it's an interesting algorithm that you can implement yourself, for example.
Yep, yep.
Okay, I don't see any more questions, so we will be wrapping up. Thanks, guys, again for joining today, and see you the next week.
Yeah. Bye bye. Have a nice day.